I'll start sharing. I think I'm already sharing the screen, but I'll put the file on the screen. Can you see it now? Can you?
Okay.
Yeah. So first of all, thank you very much for inviting me. It's a pleasure to see so many old friends. And this topic is not very close to anyone belief. But I also was not working on it for long, but I thought it might be of some interest. This is kind of what I was doing for the last, among other things, for the last year or two or three. Uh, so, what is it about? Joseph Stampfli was a mathematician. I just learned about him rather recently. From Indiana, who wrote this paper in 1970. He was born in 1932, and he lived quite a long and productive life. Most of his life at the University of Indiana, which was a very good place for operator theory, especially at the time. In particular, Paul Halmus, who everybody knows, was chairman at the time. He was there from 1969 to 1985. These were good years for operator theory. And the paper is actually, well, the talk is actually not about what the title of his paper was, the norm of a derivation, but I feel like I'll have to explain at least a little bit what his paper was mostly and how it is related to what I will be talking about. So, by definition, the derivation on any Banach algebra is an operator defined as follows. It acts from A to A, and it satisfies this property of a derivative. That's why it is called the derivation. When applied to the product AB, it is A times the d of B plus d of A times B. In particular, this property holds for this operation d sub t defined on operators on some Hilbert space, which is basically a commutator with t, at minus ta. And this is called an inner derivation. And as it happens, under certain additional conditions, not very restrictive, this is the result of Sakai, 1966. Actually, this describes all possible derivations. So every derivation is an inner. And the property of this operator, which Stampfli was interested in particular, was computation of the norm of this operator. It's an obvious property that the norm of d sub t does not exceed twice the norm of t. If you think just a little, if you subtract any multiple of the identity from t, you get the same operator. D sub t is the same as d sub t minus lambda identity, and therefore the norm of d sub t will not exceed the infimum of the norm of such differences over all complex numbers C. And the non-trivial, not very difficult, but still non-trivial result by Stampfli, the main result of this paper, is that
I'm sorry, Ilya Matveyevich, somebody else seems to share the screen.
Don't see the presentation, just an announcement on seminar.
Yes.
Okay. Well,
Amiran, I suppose, he's sharing his screen.
So he should stop sharing, I suppose.
Adjust him.
Should I go back?
Yes, yes. Now you can
so
show
how far back should I?
I'm sorry.
From the very beginning?
No.
No?
It was just a couple of seconds ago.
Okay.
But
So
we cannot see it now.
So is everything okay now? Can you see my screen?
No. Please share it again.
All right. I thought I was sharing it, but let's check. Well, it says that I am sharing the screen. So can you see my screen?
Well,
I don't see, just a capital letter I in the circle.
Right.
we guess that you
Okay.
you're trying to share it, but
Can you see the screen now?
yes.
Yeah.
But no
No, I
presentation.
understand. This will be back shortly.
Yeah.
Well, okay, now we
So
see.
should I go back, start from the very beginning? That's not that much.
No, it's okay from here.
From here. So
Yeah.
once again, well, just a little bit back. So this is the definition of the derivation defined by the linear operator T, commutator AT minus TA. We're interested in the norm of this operator. It definitely does not exceed twice the norm of T. Since the operator does not change when we subtract lambda times the identity, it will not exceed the infimum of norms of T minus lambda identity over all possible lambda, but this is the first result by Stampfli. In fact, this is not the infimum, it's the minimum, and there is the equality. So that's the formula for the norm. And that's why it is interesting to find a point lambda at which this minimum is attained. And this is what Stampfli called the center of mass. We decided for some reason that this is not quite a good name. The reason will become later, cleared later, and the term we propose is Stampfli point. And that would be our notation for it. Okay, it's not that hard, once again, to figure out because everything is invariant or behaves rather nicely under translations, that lambda naught is the Stampfli point of A, if and only if the Stampfli point of A minus lambda naught identity is 0. So the first question, which we will be talking about, can be stated as describe A for which the Stampfli point is 0, or slightly more generally, but that's basically the same thing, compute the Stampfli point of A if possible. Okay, what else Stampfli figured out in his paper was that a certain set is helpful when considering this Stampfli point. The notation is W naught of A, and this is a definition which looks somewhat artificial, but we will see what other relations are. Lambda, by definition, belongs to this set, W naught of A, if and only if there exists a sequence of unit vectors in the Hilbert space H, such that when you take scalar products AXN with XN, they converge to lambda. This is our lambda. But on top of that, the norms of AXN converge to the norm of A. So basically, we are approximating the norm of A by the sequence of vectors X and N. A related notion, which is very well known and interesting and nice, and I could talk hours and hours about it, but I will not, is the numerical range of A, which is similar. It is there is no requirement on the behavior of the norm of AX. Just we take the set of all scalar products AX with X still being the unit vector, let X travel all over the unit sphere in H, and what we get is the numerical range. And the other term for it, except more acceptable in Russian literature, was the Hausdorff set, as some of you might remember. And the relation, well, since they are related, the W naught of A is called by Stampfli the maximal numerical range. And Stampfli's claim is that, and here are two implications, that if the Stampfli point in our terminology of A is 0, then 0 is a point in the maximal numerical range, and moreover, if 0 is a point in the maximal numerical range, then not only the Stampfli point is 0, but more than that, the norm of A squared plus absolute value lambda squared does not exceed A plus lambda, the norm squared. You probably see that this condition on the right is, formally speaking, stronger than one on the left. But because of these implications, as it happens, they are equivalent. Which in particular, in passing, by the way, proves that the Stampfli point is unique. There is no reason to believe in that a priori, but that's how it is. I will not, my intention was to prove one of these implications, and I still intend to do so, because it's a nice and simple proof for the second implication. The first is a little more involved, and here is how it goes. And from there, it will be clear why the maximal numerical range is being defined the way it is. So we are given that 0 is in the maximal numerical range. So we have a sequence xn such that axn goes to 0. The norm of axn goes to the norm of A, and that's exactly what's written here. Take these vectors x and n, x and x goes to 0, norm xn goes to norm of A. And then just simply compute A plus lambda identity times xn, the norm squared. If you write it to the scalar product of this vector by itself and rewrite it, expand the usual way, what it will be equal to is the norm of axn squared plus absolute value lambda squared plus twice the real part of this thing. And axn goes to 0, therefore this thing will go away, and we will have convergence to the norm of A squared plus absolute value lambda squared, and that shows that the norm of A plus lambda identity squared is bigger than or equal to this limit, and we're done. So that's indeed a very simple proof. And the other implication, as I already mentioned, is slightly more involved, but still doable and true. And therefore, indeed, if we want to find the Stampfli point, what we need to do is find the maximum numerical range and figure out whether or not 0 lies in it. Okay, that's why it is interesting to find the maximum numerical range. And what else was observed by Stampfli in this paper of his, that the maximum numerical range is a convex closed subset of the, I'm sorry, there is one thing missing, not necessarily of the numerical range itself, but of its closure. In general, the numerical range is not necessarily a closed set. It is in finite dimensions, but not in general. And by the way, the numerical range itself is also a convex set. This is a very well-known Toeplitz-Hausdorff theorem. And if the dimension of H is finite, there is a very simple description of the maximum numerical range. Not that it's very helpful in finding it, but at least it shows the relation. This is what one needs to do. Compute A star A find the maximal eigenvalue of A star A, take the respective eigenspace, this is L, compute the compression of A onto this subspace. That is, by definition, consider A on L. L is not necessarily invariant under A, so we will compress it back by applying the orthogonal projection onto L. This B is an operator acting on L. Well, it is an operator, it has its own numerical range. Its numerical range is the maximum numerical range of A. And then it was very clear and obvious in infinite dimensions why the set is closed, why is it convex, and why is it a subset of, in this case, the numerical range itself. Still, the question remains, what exactly is it? And that is the second question, and these two questions are interrelated, and these are the questions I'm going to discuss. All right, everything is crystal clear in case when A is normal. That's a reminder that normal means that A and A star commute, and this in particular implies that A minus lambda identity is also normal. And then the numerical range can be described in terms of the spectrum of A. This description is somewhat subtle, but if we are just interested in the closure, it's very simple. It's just the convex wall of the spectrum. And the norm of A is the supremum of the absolute value of the spectrum. And this all is still true if we subtract lambda. And therefore, everything is no. This is what's happening. You have to draw the spectrum of A, whatever it is, then find the minimal circle, that is the circle of the minimum radius which contains the spectrum. The center of the circle is the Stampfli point of A. And the maximum numerical range of A is what you get as if you do the following. You take the points which are in the spectrum of A and on this circle, and there are some. You take the convex hull of this thing, which is, of course, a subset of the numerical range, because spectrum, I failed to mention that, but it's true, spectrum is contained in the closure of the spectrum is contained in the numerical range, in the closure of the numerical range. So W naught of A is the convex hull of this thing. And on the next page, I believe, is my attempt at drawing the picture. Yeah. I'll get back to the previous slide, but for now, enjoy the picture to the best of my ability. The green thing is the spectrum, and these green dots are also in the spectrum. The blue circle is this critical circle, which is the minimal circle containing the spectrum. The black rectangle, not the rectangle, the black thing is the boundary of the numerical range. So whatever is inside is the numerical range. And the red thing is the boundary of the maximum numerical range. And it's not clear from the picture where 0 is. So if 0 is inside the red thing, the Stampfli point is 0, and if not, it's not. Yeah, this is how it works. Okay, this all was implicitly or explicitly in the paper of Stampfli. And so what's new? Well, one of the results is that this actually extends to subnormal operators. And that's my result, published in Operator and Matrices in 2019. And then almost immediately it was extended even further to hypernormal operators. And I will explain on the next slide what this all means. That was done by Baghdad and Kaadout, two mathematicians from Morocco. And just to entertain you, where did it go? This takes time. I'm not sure what is happening.
Так,
Yes.
что-то не...
Can you see it now?
Yes, we can.
Okay, so this is one of them. This is the other of them, and this is me. The picture was taken in Marrakesh, Morocco, and this result, which I just mentioned, is actually the high point of the PhD thesis of this mathematician on the left. The mathematician on the right is his PhD advisor. They were in the same graduating class, but somehow it happened. And this mathematician on the right, besides being a mathematician, is also an owner of 3 leather shops in the old market in Marrakesh. And this is one of these shops. So this is something which you cannot have with online meetings or online PhD defenses. This was last year. Okay, back to business at hand. Well, here is a reminder of what is subnormal and what is hypernormal. Subnormal means that A is our operator, and somehow you can make it into a block of a normal operator. So you can construct a bigger Hilbert space and 2 other operators, C and B, and this is our new operator N, and A is a restriction of this A on some invariant subspace, and N happens to be normal. And there is a whole theory of subnormal operators. And of course, normal is subnormal, but not the other way around. Hypernormal in its turn means that A star A minus A star is positive semi-definite. The normal, let me remind you, means that A star A equals A star. So hypernormal is normal. Normal is hypernormal, but not the other way around. As it happens, subnormal is actually in between. This is all very nice, but in the finite dimensional setting, they're all the same. So there is nothing new here. In finite dimensions, this is interesting only in infinite dimensions. Okay, what else? Yet another result, which is of some interest. Well, suppose we're not normal or not subnormal. And we know that the maximum numerical range, it lies inside this circle. It lies inside the regular numerical range, or rather its closure. Does it have intersections with the boundary or not? Or does it lie completely inside? Well, this is something which can be settled, and the answer to this question was found. And as it happens, this is true if and only if the operator is what is called normaloid. In particular, it is true for all 2x2 matrices, but it is not necessarily true starting with 3x3 already. And this is an example when it is not true for 3x3. So here is the situation here. If we take this 3x3 matrix, what is normaloid, by the way? Let me remind you, it means that the norm is equal to the spectral radius and at the same time, therefore, equal to the numerical radius. And this operator is actually of this kind because its spectrum consists of 2 points, 0 and 1, and its numerical range is this thing in yellow. It is the convex hull of the circle centered at 0, radius 1/2, and the point 1. And therefore, indeed, the spectral radius is 1, and the numerical radius is 1. And, well, if we compute this subspace on which maximum norm is obtained, it's two-dimensional. It is the span of two vectors E2 and E3, and therefore the maximum numerical range is this 0, 1 interval. And if we take this circle centered at 0 with the radius, which is the spectral radius, the only point in common of the spectrum and the circle is 1. And therefore, the convex hull of the set is 1.1. And this is not the same as the maximum numerical range. So the maximum numerical range can be bigger than this convex hull. Here is a comment which I will illustrate by what follows. We all know that situation in one-dimensional case and in several variables is very different on many occasions. But as it happens, and as some observations show, it is also true that sometimes the situation in 2x2 cases, and those which can be reduced to 2x2, is very different from what happens when the dimension is bigger than 2. So more to illustrate this point will follow. So here are some results on computation of the maximum numerical range. These are from my joint work with Hamed Ali. Well, first observation, everything is nice and clear for 2x2 matrices. The maximum numerical range is then a point, and what point exactly I will illustrate in a minute. And this result can be extended to many situations which are formally speaking in higher dimension, but in fact everything boils down to 2x2. Here are these particular cases. If A is of any size, but of the structure as shown here, it's a block matrix with diagonal blocks being scalar multiples of the identity, two other blocks x and y, such that if you take the product xy and yx, they are both normal, then everything boils down again to the 2x2 case. And that covers in particular the so-called continuant matrices or quadratic operators. Quadratic operators are operators acting in any dimension but satisfying the quadratic equation. And that also covers the situation when L, let me remind you what L is. It is the eigenspace of a star A. So if the eigenspace of a star A has codimension 1, then everything can also be figured out. And that, of course, also into some sense an extension of the 2x2 case, because in the 2x2 case, you're either normal when the dimension of 2 is 1, when the dimension of L is 2, or if the dimension is 1, the codimension is also 1, and nothing else is possible. So I just told you what these results are about. I can show them if you want to see them, how they look. Well, can you see this page?
Yes, more or less.
Right. Okay, so this is just to illustrate that things are rather complicated already in the 2 by 2. So this is a 2 by 2 matrix, which is not normal. If it is normal, well, the situation for normal is clear. You just have 2 points in the spectrum, and everything depends on where is 0. If one of them is closer to 0 than the other, then the point which is further away is your maximal numerical range. If they are equidistant, you connect them by the line segment. And that's your maximum numerical range. If it is not normal, the maximum numerical range is just 1 point. And this point is Z0, and that's the formula for Z0. Lambda 1, lambda 2 are, of course, the eigenvalues, and T0 is this number. Okay. This is the picture. This is yet another picture. And this is what happens when you are 3 by 3, but the numerical, the dimension of L is 1. I'm sorry, the dimension is 2, the codimension is 1. This light yellow thing is the numerical range. This dark yellow thing is the maximum numerical range. This is one possibility, this is another possibility, this is yet another possibility. Okay, this is all about the, by the way, I have never asked if there are any questions. Maybe it's a good time to do so, or maybe it's already too late. So let me just wrap up this thing, this part. This is all about the paper with Hamed. What was done there? We have computed maximum numerical range in some cases. Generically, it's a point. But where is this point is a good question, and it's not always easy to answer. Any questions so far?
Probably, if I may, where this derivation, in fact, enters?
Nowhere.
Okay.
I didn't say it would be a talk about derivations. It will be a talk about a paper by Stampfli, which was on derivations. In this paper, Stampfli introduced 2 notions, the center of mass, which we now call the Stampfli point, and the maximum numerical range. And the talk is about the Stampfli point and the maximum numerical range.
Okay, thank you.
Yes, I'm glad we have that out of the way. Let's move on. So here is the other part. Now we want to search for this Stampfli point. And these are results joined with quartz mostly. Once again, n equal 2. What happens then? Then the answer is simple. It's not contained in paper by Stampfli, though I'm sure Stampfli knew the answer. And later on, well, we thought it's our result. This paper is not published yet, it's submitted, but the preliminary version can be found on arXiv. And there, well, it's stated as a lemma, I believe. But then we found out with some outside help that actually, in passing, this result is stated in a paper by Stolov, or Stalov, I'm not sure, in Izvestia Vuzov, 1979. So the result is as follows. For any 2 by 2 matrix, the Stampfli point is the middle point between the eigenvalues. So indeed, it is the center. It is the center of the spectrum, and at the same time, it is the center of the numerical range, if you wish, because the numerical range of any 2 by 2 matrix is an ellipse. an ellipse with the eigenvalues being the foci of this ellipse. And therefore, the center of this ellipse is indeed the center of mass and the Stampfli point. Again, this result extends, I wouldn't say easily, but it does extend to quadratic operators and to any operators even in infinite dimensional setting if it is representable in the block diagonal form, with the diagonal blocks being scalar like this, x and y completely arbitrary. And again, the Stampfli point is in the center. It is this alpha. And this covers, in particular, operators which can be represented as tridiagonal matrices with constant main diagonal. And then this entry on the main diagonal is the Stampfli point. So everything seems rather natural. But things get more complicated if we move away from 2 by 2 or results which can be reduced to 2 by 2. And well, here is a continuation of the thing. Here it says recall, but I don't think I mentioned it before, so I'm just telling you right now that once again, it was proved by Stampfli himself that this point lies in the closure of the numerical range. And as you might remember, the closure of the numerical range contains the convex hull of the spectrum. But does the Stampfli point, is it contained in the convex hull of the spectrum? It is for normal operators and therefore for subnormal and upper normal. But not in general, as it happens. And once again, Stampfli mentioned that in his paper. He did not provide any examples, but I'm sure he knew examples. Doesn't happen for 2 by 2, because for 2 by 2, it is the middle point of the spectrum, and therefore it is in its convex hull. We will see later on that it may happen for already 3 by 3. But it does not happen, and that is the next result. It does not happen if A is almost normal. So here's the theorem. If A is almost normal, then its Stampfli point is contained in the convex hull of the spectrum, which is good to know. I will explain what almost normal means in our setting, and there are many definitions of almost normal. One definition which we are not going to use is as follows. Normal means that A star equals A star A. That is, A star A minus A star is 0. So almost normal naturally means that A star A minus A star is small. In what sense small? Well, in some sense. Let's say the rank is 1, or finite, or compact. All these definitions are in use, and they're all variations of almost normal. But this is not our almost normal. Our almost normal is as follows. This is the definition which I believe in the finite dimensional setting was introduced by a person whose name escapes me in a moment, but it will come back to me. And in finite dimensional setting, well, here is how this definition goes. Yet another definition of normality is that a matrix is normal if it has a basis consisting of orthogonal, a basis of eigenvectors, which is orthogonal. So if it has n orthogonal eigenvectors. Almost normal is if it has n-1 orthogonal eigenvectors. And the nth one, who cares? So that's his definition. We want to extend it to the infinite dimensional setting, and then I think the way to state it is there is an invariant subspace of codimension 1 on which our operator is normal. So this is our almost normal. And if you think about it, of course, for n equal 2, everything is almost normal, because you can find one vector which is orthogonal because it has nothing to be orthogonal to. All right, and the statement was already made, and if there is time and desire, later on I will show the proof, but we'll see if it comes to it. The proof is not easy, and I like it. But here are some other results for 3 by 3, but not almost normal. Even for 3 by 3 matrices, we don't have an answer in general. And the only case in which we have some kind of an answer is when the spectrum of A is just one point. So every matrix can be put by unitary similarity into an upper triangular form. This is what we're doing here. And the spectrum is then on the diagonal, and whatever else is, if you want, is upstairs. Here is one statement. And the convex hole of the spectrum is, of course, lambda, if they're all the same. And the claim is that this Stampfli point is lambda if and only if at least one of these numbers x, y, z is 0. So this is if and only if the condition that the Stampfli point is contained in the convex hole of the spectrum holds for these matrices. And if it is non-zero, then we do have a statement, and you will see in a minute what the statement is, but it's not pretty. The claim is as follows. If x, y, z is not equal, my apologies again, it was supposed to be 0, not lambda. Let me correct that. Then the Stampfli point of A is lambda plus zeta. Zeta is a number, not surprisingly. Here is the argument of this number. That's easy. X, y bar times z. And it is defined uniquely up to 2 pi because this is non-zero. And there is a formula for the absolute value of z, which I will show in a minute. So I'm done with these slides. I'm going back to the PDF file now. Here is the proof for almost normals, which we will get back to if we want to later. And that is the theorem for which I was just referring to. So once again, you can see the screen, right? Hopefully. So A is this matrix. As you remember, x, y, and z are the numbers in the upper part of it. This is the Stampfli point, lambda plus zeta. Argument is, as I already mentioned. And that's the formula for the absolute value of zeta. You just need to compute this polynomial of degree 5. Nice polynomial. As you can see, the coefficients of this polynomial are in terms of u, v, and w. U, v, and w are simply the absolute values of x, y, and z. This is polynomial of degree 5. As it happens, it has either 1 or 3 positive roots, and the absolute value of z is a positive root of this polynomial. If there is only one such positive root, then that's it. if there are 3 roots in all our numerical experiments, it was the smallest one. But we don't have a proof that it is the smallest one. We conjecture that it is the smallest one. And what you can do is compute all 3 and check and see which one works. There is one particular situation in which things are slightly better. This is the situation when x and z have the same absolute value. Then we do have the explicit formula for absolute value of z, which is right here for your viewing pleasure. V and u, let me remind you, are absolute values of x and z, and there are 2 cases depending on this strange number. And in particular, even furthermore, if x, y, and z have all the same absolute value, then this is what absolute value of zeta is equal to. So this is all very strange and shows how fast things get more complicated when passing from 2 by 2 to 3 by 3. And here are some more pictures. So this is, there are several particular cases. So this is the 3 by 3 matrix with 3 diagonal entries coinciding. And then, as we know, the Stampfli point should be in the same place, and there it is. And the numerical range, by the way, then is the circle. Here is a picture for some other situation. This is, by the way, when the diagonal entries are not the same. But the Stampfli point still lies in the converse of the spectrum. This is the spectrum, and this is the Stampfli point. And there are some other pictures. This is the one for a 3 by 3 matrix with coinciding eigenvalues. This is 0, I suppose. And this is the Stampfli point, which is elsewhere. And in this case, the numerical range has a flat portion on the boundary. And this happens if and only if, by the way, when absolute values of these 3 entries are all the same. And this is yet another picture. Once again, 3 diagonal entries are the same, equal 0. One of these points is 0. I think this one is 0. No, this one is 0. And this is the Stampfli point, which is different. And the numerical range here is different. It's not circular. It's not, there is no flat portion on the boundary. This is the so-called ovular numerical range shape. So yes, this is how we learn how to compute the Stampfli point and the maximum numerical range in the 3 by 3 case. I know it sounds pathetic, 3 by 3, but well, things are complicated enough even then. Let me go back one more time to this slide, and here's the last one. Thank you for listening. I'll stop here.
Thank you very much for a very interesting talk. Thank you.
Thank you.
And please, if there are questions. Please remember that your microphones are muted. So if you have a question, please unmute the microphone.
I'll stop sharing for now. I want to say one more thing.
I see that there is a question, yeah, from Professor Sitnik.
Okay.
По-русски нельзя задать вопрос? Это запрещено?
Я еще понимаю по-русски.
Да я помню, я же вас недавно видел относительно в АМАД, поэтому, Илья, я помню. У меня одно такое небольшое, не то что замечание, вот у вас там есть элементарное выражение «корень из-под корня».
Корень из-под корня?
7, его можно немножко упростить по формуле сложного радикала, потому что там есть правило, когда это можно делать. Там получается 49 минус 48, 1 точный квадрат. Но можно представить в виде разности простых корней без двойного. Ну, это просто. А вот более не то, что серьезное, а вот я бы хотел разобраться, может быть, вы поможете в таком вопросе. Вот насколько много вообще вот того, что вы называете Derivation, да? Вот, например, если взять пространство C1, то там описание всех операторов, которые удовлетворяют правилу Лейбница первого порядка, оно известно, это только производная, умноженная на функцию, и все. Вот в таких ограничительных теорем в произвольных банковых пространствах или более общее, нет ли описания вот всех таких операторов в банковых пространствах, хотя бы каких-то конкретных и известных? Спасибо.
Okay, I will translate the question for the benefit of others, and then I will tell you that I don't know the answer, but I will say something at least. So the question was if there is a description of all the derivations in other settings, and well, as I mentioned earlier, there is, in the very beginning of the talk, there is a paper by Sakai, in which the conditions are, it's the paper of 1966, so rather old. There are listed conditions, rather mild, under which the only derivations are the inner ones. That is commutator operators. This is not the case in general, and I don't know, because this is honestly not what I work with, if there are any questions and if there are any answers in other settings, but it is definitely a good question. So I'm not an expert on that, but we can talk about privately. And I will simplify the double root. As I said, it's not published yet, so yeah, thank you for the suggestion.
Other questions? You see that all questions are around the derivation. So yeah. I have one more. What was the reason that Stampfli considered in his paper just that case? What was his motivation? Let's see.
Why derivations at all, or why this particular derivation?
Well, I suppose this particular derivation.
Okay. Well, the reason why he considered this particular derivation was because this is the only possible derivation. If you consider the C-star algebra, which can always be realized as the algebra of operators acting on Hilbert space, then the only derivations there are of this kind, commutators with operators. Mm-hmm. And that's why he proposed that. Why derivations are of interest, well, I cannot answer. It's an interesting question. As I said, these were golden years of operator theory, and whatever operators they would get their hands on, they consider.
Okay, thank you. Alexey, do you have a question? Your microphone is muted.
Sorry. So I just have a very general wondering also about this derivation. We know that derivation is a kind of a bad operation, and we don't expect after differentiating, you don't expect to have a good something function or operator or something, right? So what's the reason of, maybe it's a very general question, but what's the reason application to have the norm of this derivation operator, which is quite a very difficult task to get it.
Well, once again, I was interested mostly in the objects which arose in this paper, the maximum numerical range and the center of mass, not the derivation per se.
Okay. So if there are more questions.
Well, that talk was very clear.
Yeah, right. So two things I wanted to say in conclusion. Number one, I want to thank you again for this opportunity, well, Alyosha in particular, for this opportunity to give a talk to so many good old friends and new friends as well. And secondly, maybe some of you have expected something closer to things I was working on before, such as factorization of almost periodic matrix functions. Unfortunately, there was not too much progress on that. So there were some little tiny steps, but not much. And if anybody is still interested in joining me in this adventure, the help would be much appreciated. Yes, so people which I'm working with now, they're of different types.
Okay, thank you very much again.
Maybe we have time.